This is fundamental problem 5 from chapter 19. The 50 kilogram spool is subjected to a horizontal force of 150 newtons. If the spool rolls without slipping, determine its angular velocity 3 seconds after it starts from rest. The radius of gyration of the spool about its center of mass is 175 millimeters. So we can use the impulse momentum relationship for linear momentum and also for angular momentum. And for linear momentum, we can apply this in the x direction and also in the y direction. You don't have any acceleration in the y direction, so if you look in the y direction, that would just tell you that the normal force is equal to the force of gravity. And in this case, we're not really even going to need to use that, because if it's rolling without slipping, we have a static frictional force instead of a kinetic frictional force. And we can only use the normal force times the coefficient of friction to find a static frictional force if we know we're at the maximum value for the force of static friction. So we're just going to use this in the x direction. So the first thing that I should do is to draw a free body diagram. So I have the force P here and a force of static friction, which I'm going to assume is going in the positive direction. But if that happens to be incorrect, then I should get something negative for the force of static friction. And I think we saw something like that before in a previous problem. So if we have the force P here, the rotation would be this way, which is usually the negative direction, but let's call that the positive direction in this problem for the rotation. Okay, and then we're going to be using this equation here. And the initial velocity in the x direction is 0 because we're starting from rest. So we have 0 is equal to, or plus, the sum of the forces in the x direction. So I have this force of 150 newtons plus the force of static friction. And then I'm integrating with respect to t, but I can ask myself here, are these forces dependent on time or are they constant? Well, these forces are not changing in time. The force P is staying constant at 150 newtons. The static frictional force is not changing. So when I do the integration, the net force can come outside. Then I'm just integrating with respect to time from 0 to 3 seconds. So that just gives me a 3. And then this is equal to the mass times the x component of the velocity at event 2. So for the velocity of the mass center here, because the spool is rolling without slipping, we can say v g x is equal to, this is the point that's touching the ground. We'd use the outer radius for the distance from the mass center to that point. So that's 0.3 times the angular velocity. So this is 0.3 times the angular velocity. And the mass is equal to 50. So this is 50 times 0.3 times the angular velocity. So that's 15 times the angular velocity. And let's solve this for the force of static friction. So if I divide both sides by 3, I get 15 divided by 3, which is 5. And then bring the 150 over to the other side, and you get the force of static friction is equal to 5 times omega minus 150. Okay, so that came from looking at the impulse momentum equation for linear momentum in the x direction. Okay, now we're going to look at the equation for angular momentum. And we're going to say that this is the positive direction when we use this equation here. And this is the direction for the angular velocity. And my initial angular momentum is equal to 0 since the spool is initially at rest. So I have 0 plus the sum of the moments integrated with respect to t. So I have this force P here acting at a distance of 0.2 meters, and that causes rotation in what I'm calling the positive direction for this problem. So this is my force P is 150 times the distance of 0.2. Let's just say here this is using equation 1912. Okay, and then the sum of the moments, so if I look at the force of static friction, that would cause rotation in this direction, which is the negative direction. So minus the force of static friction, and that distance from here to here is 0.3. That was the sum of the moments. Now I integrate with respect to t, but this can come outside the integral since everything that we have here is constant. So when we integrate with respect to time, we're just going from 0 to 3 seconds, so everything here gets multiplied by 3. Then, for the right-hand side of the equation, we have the moment of inertia times the angular velocity. For the moment of inertia, they gave me the radius of gyration. So remember that if we're given the radius of gyration, the moment of inertia is the mass. The mass is 50 times the radius of gyration squared. The radius of gyration is 0.175. And then this is times the angular velocity. Let's simplify this a little bit. So 150 times 0.2 is 30. This is minus the force of static friction times 0.3 times the 3 that we had here, which is the change in time, is equal to, this is 1.531 times omega. Okay, now I have an equation for the force of static friction. I'm going to take that and put it in here. So now I have 30 minus 5 times omega minus 150 for the force of static friction. This is being multiplied by 0.3, and that's all times 3, and that's equal to 1.531 times omega. Okay, now we can solve for omega. And you can finish that on your own if you want to fill in the missing work. And you should get 37.31 radians per second. I guess the last thing that you can do, since we assumed this was the direction for the force of static friction, you can take this and put it back in here. And if that gives you something positive for the force of static friction, then we're good. So that does. So it all checks out. And that concludes fundamental problem 5.